Hey, what's up? We are jumping into our next section where last time we talked about an introduction to hypothesis testing. Today we're going to see, at least start to see some ways in which we can do that. And we're going to do this for a very specific kind, right? So we're going to talk about hypothesis testing for population proportions, right? So let's review just a little bit on how we've used population proportions in the past, right? The idea is that we have some type of a population, right? And we ask some type of a question to the entire population, right? Maybe it's a yes or no question, I don't know, but it's some type of a question which has some options on it. And we have certain proportions that say yes, let's call that P naught, certain proportions that say no, let's call that P1 maybe, right? So for instance, let's say we ask them some type of a question and 60% of the people would say yes. Then P naught would be 0.60, and if they 60% say yes, 40% say no, that'd be 0.40, right? So again, the idea is that we're trying to figure out what that number actually is for the population. All right, so let's say we have, and if you remember the notation, capital N represents the population size, right? And we don't want to ask everybody in the entire population, right? So what we've been doing is we've been taking a sample, right? And the sample has some size, let's call it little n. And what we're trying to do is we are trying to estimate this particular value right here, right? So the proportion is equal to whatever number P naught happens to be, right? So what we do is we take our sample of size n, and what we do is we count the number of yeses we have and then turn that into a proportion, right? So if x equals the number of yeses that we get in this sample, then P hat, which is the proportion we get from the sample, also known as the sample proportion. The way we do that is we just take that number x and divide it by my sample size, right? So in other words, if I have this sample of size 75, if I get 25 yeses, then P hat would just be 25 over 75, which is 0.33, right? So that's how you can calculate that sample proportion, right? Of course, the question is that sample proportion actually close to what the real value is for the population, right? Well, we've been asking that question, and we'll get our way around to it. So let's remind ourselves some of the things that we've been doing here. If you remember, if we pull out a whole bunch of different samples on here, right, we can create what's called a sampling distribution, right? So all those samples, of course, will have the same size. Let's call it n, right? So what's the sampling distribution for all samples of size n look like? Right? Well, if you remember, we've got some checks that we can do, and if all these checks pass, then this sampling distribution is close to the normal approximation, right? And here are those checks that we did, right? First of all, make sure that you use a simple random sample, right, when you collect your data. The second thing is we looked at a number, n times p times 1 minus p, and made sure that it was bigger than or equal to 10, right? And something that we said before, but we didn't check a whole lot, but now we'll start to check it with a little more regularity, is we want to make sure that the samples are independent, right? And sometimes that can be pretty tough unless the sample is nowhere close to the size of the population, right? For instance, if I have 30 people in a room, right, and I take a sample of size 10, the odds are that one person can really affect what another person thinks, right? But if I have 1 million people in my population and I pull out a random sample of size 30, the odds are they're not associated to each other at all, right? So as long as the population is a lot bigger than the sample size, we're okay, right? And that number that we're going to use is actually 20 times larger. So here's the check that we do here. If n, little n, the size of the sample, is less than or equal to 0.05 times capital N, the size of the population, then it's so spread out that we can pretty much assume that it's going to be independent, right? So if we have these three properties, and we'll be checking them throughout this lesson, then all those samples are close to having what's called the normal distribution, right? So when you think about the normal distribution, you think about the mean and the standard deviation. Right? The mean of these things is just going to be the mean of the population, right? In which case is just P naught. And if you remember the standard deviation, the way we calculated that is that was just P times 1 minus P over little n. All right, so this is stuff we did back in chapter 9, right, where we looked at a sampling distribution. Okay, so what we're going to do is we're going to use these ideas we developed in chapter 9 and extend them to testing these hypotheses that we started looking at in section 10.1. Right? So there are two ways that we're going to try to test these things. Right? So we have two tests that we're going to do, and we're going to break this up into a couple of different lessons. So we're going to take this section 10.2 and break it up into a couple of different days. Right? The first test we're going to use, right, is what's called the p-value approach. Right? And for the p-value approach, that's where we use the normal distribution to help us figure out if we can accept or reject our null hypothesis. And the second style we'll use is what's called a confidence interval test. And this idea is not too bad either. The idea behind a confidence interval test is we'll create our confidence interval, and if our sample falls inside there, we accept H naught. If it falls outside, we reject it. Right? So those are going to be the two types of tests that we want to do. So let's go ahead and work on style 1 today, and we'll look at style 2 in our next class period. All right. So here's an example for you. All right. Let's say that we have 1,100 students at Transy. All right. And what I want to do is ask them a question. Right. So consider this scenario. All right. So I think that 60% of Transylvania students love having math classes. Right. Jim thinks that it probably should actually be a little bit more than that. Right. So what we're going to do is we're going to do a hypothesis test based on my assumption or around my assumption. Right? So in this case, the null hypothesis that we'll come up with is that P, the proportion of all Transy students that love math classes, is 0.60. Right? The alternative hypothesis, right, should be that P, if Jim thinks it should be more than that, then we want to do a right-tailed test that P is bigger than 0.60. Okay? All right, now, again, I don't know anything about the population, but let's do this check of those three properties to see if we can use our normal distribution stuff. Right? So, first of all, right, well, before I go to that check, let's just do this. Let's test it by, let's take a sample of size 50. Okay, and in this sample of size 50, right, let's assume that 32 people said yes, they actually love math classes, which means the sample proportion, P hat, would be 32 over 50, which is 0.64. Okay, all right, so now, can I take these samples of size 50 and apply the normal distribution to them? Right? Let's check step 1 here. Did I use a simple random sample? Yes, that's what we did right here. We just randomly picked 50 people, and that's what it was. So yes, we did have a simple random sample. Okay. All right. 2 is n times p times 1 minus p bigger than or equal to 10. Right? So in this case, n is 50, p is 0.6, 1 minus p gives me 0.4. That equals 12. So yep, that's bigger than 10. All right. And the third thing we want to check is for the independence, right? In other words, is the sample size, is that what, less than or equal to 0.05 times the population size? Well, the sample size is 50. Is that less than or equal to 0.05 times the sample size, which is 1,100? Well, if you multiply the right side out, you get 55, so that part checks out as well, right? So the samples of size 50, right? All of those samples of size 50 based on what we did over here, right? Which, if you remember, is, let's see, what is that? Our central limit theorem talks about how all these samples will have the normal distribution. The average of the normal distribution should be the average of my population, which we're claiming is 0.60. And the standard deviation of the population, right? So sigma of p hat here, should be the square root of p times 1 minus p over n. So that's the square root of 0.6 times 0.4 over 50, which gives me the number 0.069. All right, so that's my standard deviation. Okay, so this is what we are going to be working with in our hypothesis test. Okay. All right, so now before we actually carry out our testing, something we have to make sure that we do first of all, before we jump into this too far, is pick alpha, right, which is the level of significance. Right, because sometimes we have an idea in our head and we want to either prove something's right or prove something's wrong, right? So sometimes alpha could be 0.10, alpha could be 0.05, alpha could be 0.01, right? And if we don't set this ahead of time, sometimes our biases might come into play. Like, for instance, I might set alpha so high to where it passes this test, but it might fail these two, or I could set it so low to where it only passes this one, right? And if it only passes this one, but I set alpha to be 0.05, then maybe I'm disappointed by that, or I want to change the numbers around. So make sure that we pick alpha, that level of significance, before you ever do your actual computations. Right. Now, for our sake, that'll be given to us in the book, but if you're ever out doing your own statistical analysis, make sure you, for an unbiased point of view, make sure you set alpha ahead of time. Okay. So for this particular example, let's set alpha to be 0.05. Okay. All right, so now let's get to work. I know that the null hypothesis was that p equals 0.6. The alternative we're using is that p should be bigger than 0.6. Okay. We took our sample and found the sample proportion was 0.64. Right? We found that on the previous slide. Okay. So here's what we're doing. We're asking ourselves, or carrying out these computations. Right. This is kind of what hypothesis testing is based around. Right. So we've got our real-world set of data. Right. That comes from the sample. So the question we're asking ourselves is this: how likely is it to get this sample if H naught is actually true? Right? Because if it's really hard to get this sample, then that's evidence that H naught is false. And if it's fairly easy to get the sample, that's evidence that H naught is true. That's what alpha tells me. Right? So here, since alpha is 0.05, this needs to happen less than 5% of the time in order for me to reject H naught. Okay? So here's what our picture looks like. These samples of size 50 have the normal approximation with the height at 0.6 as the mean. For this sampling, for this hypothesis test, we're going to try to find the probability of getting my sample or a more extreme value. Right? So since I want the high side, I'll take this high area right here. Okay? All right, so again, what we're going to do is we will reject H naught, right, the null hypothesis, if this probability is less than 0.05, right? Because that's what we set alpha to be. Okay? Because what that would mean is that this sample would only happen 3% of the time, or 4% of the time, or 2% of the time, which is less than alpha. So we would actually reject that. Okay. All right. So let me throw one definition at you before we actually calculate this. All right. So when the observed results, what we got from the sample, are unlikely when we assume that H naught is true, then we say that the result is statistically significant and we reject H naught. Right? So in other words, if we go through this test and we wind up rejecting the null hypothesis, then we say that the results are statistically significant. All right? So are our results going to be statistically significant? Are we going to reject H naught? Well, let's just use that normal curve to figure it out for us. So let's get our z-score, which, if you remember, is the observed value p hat minus the claimed value p over the standard deviation. Right? So in this case, p hat is 0.64. P comes from the null hypothesis, that's 0.60, and the standard deviation we found to be 0.069. Right? And if you simplify all of this, we get a z-score of 0.58. Right? So then if we look that up in our charts, this has a probability of, well, from here back, that probability is 0.7190, which means this probability is 0.2810, right? So this number right here, that's called the probability value or the p-value. So this says that the probability that that sample would happen, given that the null hypothesis is true, is 0.28, which means it would happen 28% of the time, right? Which is way bigger than alpha, right? So in this case, based on this, right, since my p-value 0.2810 is bigger than alpha, my level of significance 0.05, right, the conclusion we get here is that we do not reject the null hypothesis, right, in favor of the alternative hypothesis. All right, so there's one example for you. Let's do the same question, but maybe let's ask it over at UK, right? So at UK, it's the same question we're going to ask them. Instead of 1,100 students, though, we now have, let's say, 25,000 students. Okay? And since I have so many more students, let's ask more people, right? So let's take out a sample of size 1,000. Whoops, just kidding, 1,000. Okay? And let's use the same null hypothesis that the proportion of students that really enjoy math classes is 60%, so the proportion is 0.6, and the null hypothesis is that p hat should be bigger than 0.6. Right? And let's have the same level of significance here. Let's say alpha is 0.05. Right? So again, here's this big old population. Let's pull out my sample right here. And in the sample, the number of yeses was 642. So the sample proportion p hat is 642 over 1,000. Right? So in this case, p hat is 0.642. Right? All right, so now what about the samples of size 1,000? Can we use the normal distribution here? Right? Let's do those three checks. First of all, did I pull out a simple random sample? You bet, just did that right there. Right? The second thing is, let's do the check of n times p times 1 minus p. In this case, that's 1,000 times 0.6 times 0.4, which gives me 240. That's way bigger than 10, so that one checks out. And the third one is the size of the sample less than or equal to 0.05 times the population size? Right? So here, the size of the sample is 1,000. 0.05 times 25,000. Let's see, so is 1,000 less than or equal to, if you multiply that, you get 1,250? Yes. Right? So this tells me that the sampling distribution, right, the distribution of all these samples, is approximately normal. The mean is what we're assuming, 0.60. And the standard deviation, well, let's do that over here real quick. That's the square root of of p times 1 minus p over n. So that's a square root of 0.6 times 0.4 over 1,000. And that simplifies and reduces to 0.015. Right? So there is the standard deviation. Okay. All right, so using this information, let's carry out my hypothesis test. All right, so here's my picture. Right, so again, all these samples of size 1,000 have about the normal distribution. The average of all those samples should have a proportion of 0.6. Right? For p hat, we got 0.642 for this one. Okay. So again, for this one-tailed test, I want to find the probability of getting 0.642, this value, and anything more extreme. So it'd be this part right here. Right? If it were a left-tailed test, if my p hat were down here, I'd want the values that were p hat and more extreme from the mean. So it would be this part. Right? But right now we've done two right-tailed tests so far. If I had a left-tailed test, we'd be looking for that particular region. Okay, so let's get our probability here. Let's get our p-value. All right, so my z-score is, again, p hat minus p over the standard deviation. So that's 0.642 minus 0.600 all over 0.015, and that gives me a z-score of 2.80. Now, what that gives me is, if you look up that z-score, that gives me an area to the left of 0.9974, which means this p-value is going to be 0.0026. Okay. All right, so in this case, the p-value, which is 0.0026, is less than alpha, which is 0.05. So since the p-value is less than alpha, we reject H0, right, in favor of H1. Right? All right. So there's a couple of examples of some right-handed tests or right-tailed tests. Left-tailed tests are the exact same thing. You just have to find z-scores on the other side. Right? So what about a two-tailed test? Though we saw those in section 10.1 as well. Right? So let's talk about those before we do one real quick. Right? So again, what it's going to look like is this. Right? So again, there's P. If I get P hat to be up here, then I'm going to want to come down the exact same distance. I guess negative P hat maybe there. It's not quite negative P hat, but that's kind of the idea. And what we'll do for a two-tailed test is, if alpha is 0.05, then we're going to take that probability and kind of break it up into these two tails. So instead of looking at just one side, we're going to look at this, and we're going to find this p-value, we're going to find that p-value, and add them together to get my total p-value. Okay, so here's an example for you. Let's say our question revolves everybody in the USA. All right. And we're asking some type of a question to where they would answer yes 46% of the time. So that'd be 0.46. What I'm going to do is I'm going to pull out a sample here of size 1,267. Let's go with that. And let's let the number of yeses in my sample be 559. Okay. So in this particular sample, its proportion, if you take 559 and divide by the sample size, gives me 0.441. Okay. And in this case, let's do a test where alpha is 0.10. Right. Let's do this. I want it to be a two-tailed test, right? So the claim is that the population proportion is 0.46. Since it's a two-tailed test, we're just going to say, yeah, P is just not 0.46. It could be bigger, it could be smaller. Okay. All right, so for these samples of size 1,267, let's do our check, our normal check. All right, so first of all, simple random sample. Yep. 2, if you look at n times p times 1 minus p, you get 1,267 times 0.46 times 1 minus 0.46, which is 0.54. That multiplies out to give me 314.7. Way bigger than 10, so that's good. And then the third step is, how do we actually check it? Because we don't know what the exact population is for the USA, but I know it's at least 350 million. Right? And that's easily 20 times bigger than my sample size. So yeah, it's okay. Right? So this one's okay as well. Right? So we know that that's going to be the right size. Right? So what that tells me is that the samples of size 1,267 have the normal distribution. We're assuming that it has a proportion of 0.46, and then the standard deviation of p hat, again, it'll be p, which is 0.46, times 1 minus p all over n. And if you stick that into your calculator, you get 0.014. Okay. So this is what we're going to be using to try to answer my test. All right, so let me clear off a little space here. All right, so in this case, we've got a two-tailed test going, so let's go ahead and draw my picture here. Whoops. All right, so the mean should be there at 0.46, assuming the claim is true. Right? To get my z-score, let's get 0.441, the sample proportion, minus what they claim is the proportion, 0.46, divide that by the standard deviation, which is 0.014, and this gives me negative 1.36. Right? So what I'm going to do to get my p-value is I'm going to go to the charts. I'm going to look up the z-score for negative 1.36. 1.36, I will find this area, I will find that area, add them together, and that's going to be my p-value. Right? So if you look up negative 1.36, this is 0.0869, and due to symmetry, that's got to be 0.0869, or you can look it up if you don't believe me. So that says that the p-value is 2 times 0.0869, if you add those together, which is 0.1738. Right. So the p-value is 0.1738. Alpha, if you remember, was 0.10. Right, we said that up here. So do we reject H0? No, we do not reject H0 because the p-value is bigger than alpha. Okay. So here we do not reject H0. All right, so that's the difference between a one-tailed and a two-tailed, right? For the two-tailed test, you find the p-value on one side and make sure the other side is covered as well. That way you've got either the bigger and the smaller, or the smaller and the bigger. Add them up to get your grand total for your p-value, and then compare that to alpha. Okay. All right, so here are some problems for you to get started in 10.2, and we'll do the confidence interval test next time. So in 10.2, we've got some quick ones here and then some computational ones at the end. Right? So look at 1, 3, 4, 5, 6, and 7, 9, 10, 12, 13, 15, and 18. All right, so we are chugging along. If you need some help, let me know. See you later.